Good morning, friends. Last month, we talked a lot about a subject in thermal engineering, that is thermodynamics. The next subject of thermal engineering is heat transfer, which is the most important topic for chemical engineers as well as mechanical engineers. So this class shall be common and will be trying to solve the problems asked in the previous years for chemical as well as mechanical. Friends will have around 45 to 50 hours for the subject. Theory you must have studied during third year of your BTech. Few things you may be remembering. Few things, if you see the books, it will be all right. Few things you might have forgotten. In the GATE paper, no derivation is asked. Some formulas, relationships are to be confirmed, and then mostly objective type questions for 1 mark, subjective questions which are quite simple numericals. So in the every class, first 1.5 hours we devote for the theory portion, revision part, and then we'll have a break for 15 to 20 minutes so that you get refreshed for the numericals. We have to do enough of practice for the numericals. If we solve previous year's papers, we get the ideas what type of questions are being asked. So as a whole, we try to do at least 100 questions in the class. The classes taken may be 15 to 20 lectures. That means 45 to 60 hours. Every class will devote at least 1 hour. That means if 15 to 20 lectures, 15 to 20 hours for solving the numericals. That means 5 to 7 numericals every day whenever we are having a class. So develop the habit of bringing the calculators with you. Whatever portion we study in 1.5 hours, based on that, whatever numericals have been asked, we'll be doing every day, right from today itself, so that you get enough of practice. The best book available on the subject is Heat Transfer by Holman. And most of you must have studied this book only during your BTech program. Otherwise, any book you are having, that should be okay. Those who are interested to purchase the new book, then they should go for whole man. Subject is very fundamental. Along with the application part, during the course of the discussion of theory portion and numericals, please don't hesitate. Any portion which is not clear, you must ask. If I explained once or twice, still it is not clear, and I will say, don't hesitate, still you should ask till everything is clear. During the course of discussion, any of your doubt may be cleared in 5 to 10 minutes, whereas when you start searching the books, it may take more than 1 hour. Time is very precious, hence let us make use of it in the most dedicated manner. Now, to start the subject, heat transfer. In thermodynamics, during second law, we studied heat transfer is always from a body of high temperature to the body of low temperatures. How long this heat transfer takes place? Till equality of temperature is obtained, and we use the term thermal equilibrium is achieved. We'll be studying conduction, convection, and radiation, which are called as the modes of heat transfer. So friends, we will try to devote 15 hours for conduction, 15 hours for convection, 10 hours on radiation, and then we have to study heat exchangers, for which we will spend around 8 hours. Then we have to study boiling and condensation. For that around 5 hours. $53 hours. And roughly I thought of 45 to 60 hours. So if I spend around 50 hours, it will be all okay. So our study would mean first topic, second topic, third topic, fourth topic, fifth topic. This is as per the importance of the chapters according to the gate papers for mechanical as well as for chemical. So let us start with conduction. There shall be propagation of heat. Heat means the thermal energy. From where to where? From a region of high temperature to low temperature, for which some medium is required. What may be the medium? Medium may be solid, liquid, or gaseous. It may not be only one medium, solid, liquid, or gaseous, or many mediums. One medium may be solid. Along with the solid, there could be some liquid also. There may be some gas also, or many mediums, and all of them should be in thermal contact with each other. Having, so to say, physical contact with each other. If I am having a mild steel rod and I am heating it from this side with the help of a burner. So this is the region of higher temperature. Heat will be flowing within the material. Material is solid. From the region of higher temperature to the region of lower temperature. How long? Till the entire length is at the same temperatures. That means thermal equilibrium has been maintained. Now what is the mechanism? What makes the heat to flow? This is quite simple. What we study in school. In the subject science, physics. Even in 12th we study only this. What is more in engineering? As somebody asked, what is the mechanism of this heat transfer? It could be because of the temperature, there are molecular vibrations. Due to those molecular vibrations, the heat starts flowing, the heat starts getting diffused into the material. That means it may be because of the molecular vibrations. Secondly, depending upon the material, its structure, it may be because of the free electrons which are moving and carrying the thermal energy from one region to the other region. Secondly, from the kinetic theory, we studied because of the velocity, there is temperature. More molecular velocity, more temperature, and heat transfer is taking place from the region of higher temperature to the region of the lower temperatures. This is the basic concept of conduction. Now friends, the most important law in heat transfer for conduction is Fourier's law. As per the Fourier's law, heat flux is directly proportional to the temperature gradient. What is heat flux? It is heat transfer per unit area. And what is temperature gradient? Temperature difference per unit thickness. For example, if this is a plain wall, this side is maintained at temperature T1, this side is T2. Heat transfer taking place denoted by the symbol Q. What shall be the unit for Q? joule per second. That is watt. Which is area. Area is normal to the direction of heat transfer. Imagine if this was a wall, heat transfer is taking place in this direction, area will mean normal to the direction of the heat transfer, this area and not this area. This is the area normal to the direction of heat transfer. If I consider a very thin element across which the temperature difference is dT and this thickness is dx. Then this temperature gradient shall mean dt by dx. Since it is a temperature difference, you write in degree centigrade or you write in Kelvin, it is immaterial. And thickness shall be in terms of meters. Area shall be in terms of meter square. And heat transfer shall be, as earlier discussed, joule per second or which is called as watt. Thus, my dear friends, Q upon A is proportional to dt upon dx. And Q upon A can be written as K dt by dx, where K is the constant of proportionality and is called as thermal conductivity of the material. Thus, in this equation, Q upon A is equal to K dt by dx. As we studied heat transfer is taking place from the region of higher temperature to the region of lower temperatures. That means temperature gradient shall become negative. Heat transfer is taking place towards the lower temperatures. So, a negative sign shall be used. So to say, to satisfy the second law of thermodynamics, heat transfer from higher region to lower region. Thus, very frequently we'll be writing Q is equal to minus K A dt by dx. Now friends, K we have used as the constant of proportionality, which is named as thermal conductivity of the material. Let us see its units. Q was joule per second, watt. K I am interested to know. A area, meter square. Temperature difference, Kelvin. Thickness, meters. So the unit of K becomes watt per meter Kelvin. Capital K was for Kelvin, small k is for thermal conductivity. So, this you are required to remember. This you are required to remember. It is as per Fourier's law, and fundamentally we should be clear about unit of all the terms that we use. I hope everything is okay. Now friends, let us develop the expression for heat transfers. We have seen Q is equal to minus K A dt by dx. During the course of derivation, we will have few assumptions. Normally, the students don't bother about the assumptions, and these are the things which are asked during the course of the interviews. Number one, it is steady state heat transfer. That means time is not the criteria. Properties remain constant. That means irrespective of time, properties and heat transfer remain constant. I mark the direction only in X. Heat transfer may take place in Y direction as well as Z direction. Tomorrow we will be studying in 3 dimensions. So today our explanation shall be all based on 1 dimension. When I say on this side temperature is T1, other side temperature is T2, what does it mean? So this side, this entire surface is an isothermal surface. It is not that temperature is 20, 21, 18, 19, 22 and average is 20. No. Throughout the temperature remains same. So we use the term isothermal surfaces. Now this material which we are using, its thermal conductivity may not remain same. Tomorrow we will be discussing more about thermal conductivity. We will keep on discussing more and more. So at present we are thinking that the thermal conductivity remains constant. And this entire material is a homogeneous material. And depending upon the grains in XY direction, the thermal conductivity also may vary in directions. But for simplicity, we are considering thermal conductivity remains constant. And that material we call as isotropic and homogeneous material. That means the thermal conductivity K is assumed to remain constant. Now with these assumptions, X is varying, so we keep it on one side. Temperature is varying. K we have assumed constant. A is constant. Steady state Q is constant. And then dt. Integrating dx from x1 to x2 minus k, a and q, they are constants taken outside the sign of integration, dt integrating from t1 to t2. That means if I take this as the system of coordinates representing temperature on this side and thickness x on this side, this surface is at a distance x1 when temperature is T1. The other surface is at a distance of x2 when the temperature is T2. So I get x2 minus x1 minus k a upon q into T2 minus T1. This x2 minus x1 k a q T2 minus T1. We have to write q on this side. Then the terms are k a T1 minus T2 upon x2 minus x1. Negative sign has been taken care of. Does it look nice? No. So let us try to see this heat transfer, the flow of heat. This side temperature was higher, this side temperature is lower. Heat transfer is within the material. Depending upon the material, its thermal conductivity, its structure, the heat transfer will be taking place. That means this material is offering some resistance to the flow of heat. Still, because of the temperature difference, the flow is taking place. It may be less or more depending upon the value of K. So I can imagine as if Q was flowing, this material has offered some resistance. Whatever has entered in, the same goes out. Nothing is to be retained. This was at temperature T1. This is at temperature T2. And T1 minus T2 can be written as delta T. This thickness is x2, this distance is x2, this distance is x1. So the thickness of the material, which is x2 minus x1, can be called as delta x. In electrical engineering, we studied Ohm's law. As here, flow of heat, there it used to be the flow of current. Material offered some resistance. There was electrical potential difference, that is voltage. Here it is the thermal potential difference. Current I is entering, current I is leaving. And Ohm's law used to be I is equal to V upon R. Analogous to this, we should try to write this. This is flow of heat, flow of current. Electrical potential difference, thermal potential difference upon a resistance. So I may write it as delta T upon delta X upon K A. The resistance offered by the material is delta X upon K A. The thermal resistance, a Newton, which denotes units, delta X upon K A. Delta X is in meters. K was in terms of watt per meter Kelvin. And area in terms of meter square. Is it all okay?
Sir, someone is saying it will be delta T.
Which should be delta T? What is delta T? Delta T I have written T1 minus T2. This surface is at temperature T1. This is at T2. The difference in temperature is delta T.
Sir, please repeat third and fourth assumptions.
Hmm?
Third and fourth assumptions.
Fourth assumption,
Please repeat third and fourth. Please repeat third
Repeat.
and fourth.
isotropic and homogeneous. This material is having the thermal conductivity which is same in all the three directions. Otherwise, depending upon the grain size in the three directions, their thermal conductivities may be different. So here I will say Kx is equal to Ky is equal to Kz. In general, I call it as K.
Sir, he is saying that delta T will be negative.
कौन सा डेल क्यू होगा? Q is constant. Whatever enters from here, same passes through this thickness, same passes through this thickness, same passes through this thickness, and goes out. Fifth assumption, you can say no heat is retained in the material. Q enters in, passes through the material and Q goes out. So it is not that through this dt the heat going is delta Q. It is Q.
Sir, third assumption, isothermal surface.
Isothermal surface. This was the plane wall. This surface is at temperature T1. This surface is at temperature T2. That means throughout this surface the temperature is T2. It is not the average temperature. So when the temperature remains the same throughout, we call it as isothermal surface.
Sir, why there is no time in the denominator?
That means we are studying not when we have switched on. We are studying when the change in anything is not there with respect to time. That means at 9 a.m. you read the temperature, at 9:10 you read the temperatures are same. Thermal conductivity is same. Density is same. Specific heat is same. So when the properties are same, heat transfer is same. At 10 a.m. I find 10 watt of heat transfer is taking place. After half an hour I see still the heat transfer remains the same. That means it is independent of time. When everything is independent of time, we say a steady state has been achieved. And if properties keep on changing, we say it is unsteady state. Is it okay? Now if somebody asks, draw the temperature profile for the plane wall. This is T1, this is T2, this is delta X, Q entering in, passing within the medium and going out. This is delta T. To some scale, let this be the value of T1. Say it was given 80 degree centigrade. T2 was given 20 degree centigrade. This is the value of T2. This temperature variation is linear. That means T1 minus T2 upon X2 minus X1 or delta T upon delta X. This remains constant. and this temperature gradient flow of heat is from the higher temperature to the lower temperatures. T2 minus T1 is negative. T1 minus T2 is positive. If you try to see the slope of this line, slope means tangent. Tangent means T1 minus T2 upon x2 minus x1. It should be negative. And you find that it is lying in second and fourth quadrant. Second and fourth quadrant, tangent is always negative. Okay. Let us have now the small concept for convection, because many times conduction and convection are taking place simultaneously. For heat transfer, for conduction, the mediums could have been stationary. In convection, there should be flow of medium. That means, imagine that this is a wall. Air comes from here. If the wall is at a lower temperature, now the chances are that this air, while touching this wall, may go up or may go down. This is the temperature TW, that of the wall. Let T infinity be the air temperature. If TW is more than T infinity, this air will get heated up. Hot air will become light air, will have the tendency to go up. If TW is less than T infinity, this air will be getting cooled. Cold air shall become heavy air. shall have the tendency to flow down. Here the flow is taking place. Here also the flow is taking place. That means the heat transfer is taking place because of convection. The flow of medium is there. There is a law called as Newton's law. As per this law, the heat flux is proportional to the temperature difference. Heat flux means heat transfer per unit area is proportional to temperature difference Tw minus T infinity or T infinity minus Tw. Let us imagine Tw was at a higher temperature. So Q upon A is equal to H into Tw minus T infinity, where this H is the constant of proportionality. It may also be called as convective heat transfer coefficient. So we may call it as Q is equal to H A into Tw minus T infinity. Q is joule per second watt. H we are interested to know. Area in meter square. Temperature difference in Kelvin. So H shall become watt per meter square Kelvin, or watt per meter square degree centigrade. Simultaneously, we shouldn't confuse K, the thermal conductivity, was in terms of watt per meter Kelvin. So our equation is becoming Q is equal to H A into Tw minus T infinity. If I try to write as per Ohm's law, we can write it as Q is equal to Tw minus T infinity upon H A. No. It should be 1 upon H. So that we can compare it with I is equal to V upon R. What is R? R is 1 upon H A. Let us check up the units. 1 upon H. H is watt per meter square Kelvin. Area meter square. So it becomes Kelvin per watt. So this we may call it as thermal resistance.
Sir, if the air is not moving, then conduction will be.
Then conduction will be there.
Sir, please repeat the diagram.
Repeat the diagram. This is a wall at a temperature of 70 degrees centigrade. And this air is at 30 degrees centigrade. This 30 degrees centigrade air is coming in contact with the wall at 70 degrees centigrade. The air will get heated up. Hot air will become light air, will have a tendency to go up. So, there is a flow of the medium air. Hence, it is convection. If this TW was 10 degrees centigrade, this was 30, air was coming, TW was less than T infinity, the air will be getting cooled, the temperature of the air will decrease, cold air, the density will increase, will go down. So flow of air depending upon the wall and the air temperature, we will say convection currents of air are obtained. That means air is flowing. The medium is flowing. Instead of air, it could have been water. They are in contact with each other and the flow of the medium is taking place. Same way, if water was stationary, it will be because of conduction. Now, this was a wall, air was coming in contact with it. There was some resistance offered. This 1 upon HA is the resistance. That means I could have stated that a very thin layer of stagnant air is formed. Because when air is coming in contact with it, there is a flow of air. But how about that air which is coming in contact with this bolt? That will become stationary air. So that will mean a stationary film of air is formed, offering resistance. So I can say at wall temperature this was this side is T infinity. This is offering thermal resistance which is 1 upon HA. So, finally, convection can be studied similar to that of conduction.
Sir, in conduction, this medium is always stationary.
Conduction medium is always stationary. There may be one medium, there may be number of mediums. The difference between conduction and convection is conduction, stationary medium, convection, flow of medium. If a gas is there, gas is stationary, heat transfer will be by conduction. If gas is moving, it is by convection.
Sir, how the film of stagnant air is forming?
The air which is in touch with the wall, what is its velocity? 0. That means it is stagnant. That means a stagnant film of air is formed, which is offering resistance. On the film, one side is wall temperature, other side is infinity temperature. And heat transfer is similar to that of conduction, because when the medium is stationary, it is like conduction. So that is the reason I stated that this phenomena of convection, when studied deeply, can be called as convection, conduction, and that is why I am here writing the expression for the resistance. 1 upon HA. Since the term is the resistance, earlier our resistance was delta X upon Ka. Delta X was in terms of meter, K was in terms of watt per meter Kelvin, area was in terms of meter square. Once again it is Kelvin per watt. Here also it is Kelvin per watt. Anything else? Now imagine that there is a wall on this side. Some gas is flowing. This side some air is flowing. For gas, the value of the heat transfer coefficient is Hi. On this side, it is for air Ho. This side the temperature is Ti. This side the temperature is To. This wall surface is at temperature T1. This wall surface is at temperature T2. Gas and air are flowing. That is heat transfer by convection. Wall, stationary, heat transfer by conduction. Heat entering Q, passing Q, coming out Q. The thermal conductivity of the wall is K and its thickness is delta X. We have to determine the value of Q. Ti is given, To is given, T1 and T2 are also to be calculated. So Q, T1 and T2. Three unknown. That means at least three equations are required. One equation for Q we can write by convection. One equation of Q by conduction. Another equation of Q by convection. Three equations, three unknown. We should be able to solve simultaneously. So what I can write is, number one, Q is equal to Ti minus T1 upon 1 upon Hi Ai. This was the resistance. Also I can write T1 minus T2 upon delta X upon K A. Also I can write T2 minus TO upon 1 upon HO A. So friends, HI on this side, HO on this side, AI this area, AO this area, same is the area for conduction. So AI, AO and A, they are all same. So let me write this first equation. This is Ti minus T1 is equal to 1 upon Hi A into Q. With the help of the second equation, I can write T1 minus T2 is equal to delta X upon Ka into Q. And last equation, T2 minus To is equal to 1 upon HO A into Q. Now, let us add them up. T1 gets cancelled, T2 gets cancelled. So I get Ti minus To is equal to 1 upon Hia plus delta X upon Ka plus 1 upon HOA into Q. So Q is equal to Ti minus To upon 1 upon Hia plus delta X upon Ka plus 1 upon HOA. This is Q is equal to Ti minus To upon, this was thermal resistance number 1. This was thermal resistance number 2. This is thermal resistance number 3. Which can be written as Ti minus To upon sigma or T. Add all the thermal resistances because they are in series. You can have the diagram, this resistance, or T1 or T2 or T3. This side was temperature Ti, this side was temperature T. So Ti minus To upon sum of all the resistances. By convection, by conduction, by convection. And we use a term called as overall heat transfer coefficient. That means put all the three terms together. We should have the equation Q is equal to U A into Ti minus To, which can be written as Ti minus To upon 1 upon Ua. This is the overall resistance. And 1 upon Ua is equal to 1 upon Hia plus delta X upon Ka plus 1 upon Hoa. So, any point requiring clarification?
Sir, all resistance of air covered in that station that was connected with previous. Sir, stagnant air saturated point. So someone is asking that all resistance of air is covered in that stationary bin.
There is a wall. On one side you are having air, other side you are having gases. Imagine that this wall was that of a furnace. Outside the wall, air was moving. Inside the wall, gases are moving. So for gases and air, since the flow is there, it is by convection. So this is the example which I am taking. So now we will have break, and after the break, today itself we will start solving the problems asked in the previous papers. So we will see what type of question is there, what is the language of the question, what we are expected to do. Anything else?
Sir, when overall HT coefficient is used?
Well, when a question is given like this, he asks you to calculate U. And many times U may be given. You may be required to calculate the thickness. As I stated that T1 and T2 are also to be calculated. From this equation, everything is known, Q is calculated. In this equation, you put down the value of Q. Ti was given, you can calculate T1. Here substitute the value of T1, get the value of T2. Here everything is known. So you write down the value of T2, Tu, everything. If equation gets satisfied, that means T2 is correct. When T2 is correct, that means T1 is also correct. So we'll see with the help of the questions what is the data available, what you are expected to do, and how to make use of these relationships, and how to remember these relationships. Because you will be able to solve problem if you remember it. If you cannot write the equation, you cannot solve the problem.
So in conduction, which area is taken?
Area normal to the direction of heat transfer. लिखा भी था, बताया भी था हैं कि ये वाल है, ये हीट ट्रांसफर है, हीट ट्रांसफर and this wall area normal to each other.
Sir, we have written that AI is equal to A is equal to A naught. How is it possible?
If it is if this was a wall, what is AI? This area. What is A? Area because of conduction. What is AO? This area. All the three are same. Areas will be changing if it is a cylindrical pipe. Inside area corresponding to inside radius, then outside radius. We'll solve the problems and derive the expressions. Whenever it is a case of wall, areas are same.
Sir, is there any case at which conduction takes place in gas-gas heat transfer?
Yes, if gas is not flowing, gas is contained within it. It is by conduction. I stated simply, if medium is stationary, not flowing, it is by conduction. It can be solid, liquid, gas. If there is a flow, जब मैंने कन्वेक्शन शुरू किया था सबसे पहले मैंने लिखा था it will be because of the flow of the medium, flow of the fluid. In solid there is no convection. In liquids and gases there shall be convection. I am happy that you are asking questions, but at the same time I feel whatever you had studied in BTech, that has all gone into the waste paper basket. Anyhow, I'll encourage the questions, howsoever silly it is or howsoever intelligent it is, you are always welcome.